Very good morning, good evening, good afternoon to all my dear friends and participants. Welcome back to this TQM2 lecture on the NPTEL MOOC, and we are continuing the discussion of the regression model and the factorial design for that, and this is the 20th lecture. So, that means we have another 12 lectures to go, and this is the penultimate week almost going on, because in each week if you finish 5 you can calculate accordingly. Okay. Now, coming back to the regression model, if you remember, which I will repeat, and please excuse me if I am just going through the same concepts again, but I am sure hearing that twice would not do you any harm, you will understand it much clearly. So, when you are trying to find out the beta hat, why it is a hat? Because you are trying to estimate, because you cannot find the exact value. If you found out the exact value, obviously putting that and multiplying beta 1 into x 1, beta 2 into x 2 would give you the exact value of y that you are able to predict beta y exactly. So, obviously the error should be 0. So, that means technically the average of the error should is 0, but they would be in each and every reading there would be some plus minus value. So, if you find out the average is 0, but in each reading it cannot be 0. So, hence it basically is a predicted value or the estimated value is beta hat. So, what you try to do technically is that try to minimize the error. So, now the error is basically the difference between the actual value of y and the predicted value of y, which is also equal to the epsilon error which you have said. Now, if you want to basically minimize the error, what you will try to do is conceptually you will try to minimize the variance. So, the variance of the errors would basically that you are trying to find out the best fit lines as the sum of the squares of the differences of the errors. So, that means you find out the error in each reading, square them up and add up the whole sum. So, you are trying to minimize that. When you do that, what is actually you are doing is like this. When you put the y values along with the predicted value of y, which we consider as y hat, as we we are doing it for beta hat, those beta terms would be there which are unknown, you have to find it out. So, if you want to find out the beta values individually, you have to basically partially differentiate the error square with respect to the each betas, put it to 0, find out the betas, that gives you the beta hat, and once you get the beta hat, that formula which came out was basically x transpose into x, that multiply them, you find out the inverse of that, multiplied by x transpose into the y. So, this transpose or y's which are all talking about are all vectors and matrices, not scalars. Suppose the true value is, so let us continue and with the discussion. So, true value is there are two values x 1 and x 2 which are independent one and the error is epsilon. So, where x 2, okay, now for the ease of explanation of these models, we will consider the number of factors as p by the suffix. So, initially we did mention it was k, then we said it was p and that suffix was l depending on the number of variables which are there. Now, as there are only two independent variables, it will be p suffix 2. So, that suffix would denote the number of x's which are there. So, let me continue with the discussion further. So, where x suffix 2 is a matrix of size x into p 2. So, p 2 matrix contains additional variables that are not in the fitted model, and the beta 2 is basically p 2 across 1 depending on what you think is basically the coefficients you want to find out. So, it can be shown that once you find out the expected value of beta hat. So, obviously, the expected value in beta hat in the long run in the asymptotic sense should be exactly equal to beta. So, when you try to find out the expected value of beta, beta hat, it comes out to be beta 1 into a into beta 2. So, these beta 2 are basically the external effects which are there. So, the matrix A is called in this model the Aliased matrix. So, and obviously A is given as x transpose multiplied by x 1, I am not repeating the suffix, that when you multiply you find out the inverse, multiply x transpose is x 2. So, it is called the Aliased matrix. The elements of the matrix operating on beta to identify the Aliased relationship which is existing for the parameters in the vector beta 1, beta suffix 1. So, resolution of three design models are considered to the level of 3. It is possible to construct the resolution 3 design for investigating up to k, which is n and minus 1 factors in only n runs. So, obviously, it will may be n minus 2, n minus 3 depending on the runs you are considering. These designs are frequently used in industrial experiments when you want to predict or forecast. So, design in which n is a power of 2. So, obviously, we are taking the 2 factor models also only. So, 2 to the power n or 2 to the power n minus 1 so on and so forth can be constructed by the method present earlier. So, what you have done is k minus p. So, k would basically be combinations of the number of factors. Initially, we had basically taken a, b, c, d, then we combine to find out E, F, G. So, which combinations you are going to take to find out the best so called effects from the factors would be dictated accordingly. So, of particular importance are the designs requiring 4 runs for which up to 3 factors are there, 8 runs for up to 7 factors, 16 runs for up to 15 factors, so on and so forth. So, if k is n minus 1, so you remember that it was 2 to the power k minus p. So, if it is k n minus 1, the fractional factorial design is said to be saturated, and because any more addition of the number of factors would not give you any additional benefit in trying to predict or find out the so called effect of the models. A very useful saturated model of the factorial design is the design of studying 7 factors in 8 runs, which is basically given by 2 to the power 7 minus 4. So, this design is about 1/16th factors, which basically becomes 2 to the power 7, because you have 7 factors. It may be constructed by first writing down the basic ones, which are considered which is 2 to the power 3. So, there are 3 factors a, b, c, and then associating the levels of these 4 additionals based on how you design the problem. So, these are as follows: as D as is a combination of a b, E as is a combination of a c, F is a combination of b c, and G is a combination of a b c, which means that if you have 3, so first what you do is that take 2 of them at a time. So, if it is 3 c 2, so obviously the combinations would be a c you have taken, then you have taken the a b values are there, which is D, you are basically saying that, and the last combination is basically b c, and the next stage what you will do is you will take the factors combination of 3 c 3. So, obviously it will be combination a b c. Now, if you remember, I did mention, and that was not very explicitly given in the slides, I did mention that if you increase the number of factors, that if you take, say for example 4 of them and you are trying to combine the factors, it will be 4 c 2 first combination. So, that will be a b, a c, a d, then it will go into the combination of b c, b d, then it will go into the combination of c d. Then when you combine the 3 at a time from this 4, it will be 4 c 3, then it will be 4 c 4. So, if you basically keep increasing the factors, so if you make it 5, the combinations will be 5 c 2, 5 c 3, 5 c 4, 5 c 5. So, depending on the combinations which you take, if you have k factors, it will be k c, k would be the individual one, then obviously we will come to k c 2, k c 3, k c 4 till k c k, and the combinations would obviously give you the effects of the combined factors. So, here you are considering 3. So, again I will repeat. So, D is a b, E is a c, F is b c, and G is combination of 3. Thus, the generators for the designs are a b d, a c e, b c f, and a b c g. So, depending on the combined effect which you are taking. Now, again, so as usual, first we define the factors, define the combinations, define the overall effect, and then draw the table. So, this is the general plan which we are following. So, again we will come to the table 8.19, which will have all the informations about the combinations of the factors. In the first row, we have first column, we have the run, which is the run number starting from 1 to 8. Then the basic design factors, as we mentioned, that we have taken k is equal to 3, which was a b c. Then the combination which we took, if you remember, we took 2 at a time, then 3 at a time. So, obviously 2 at a time was basically a b, a c, and b c. So, they are mentioned as D, which is a b, E, which is a c, and F, which is b c. And the combinations of 3 of them taken all at the same time was G, which was a b c. So, if you take the combinations of the effects of A being minus, B being minus, C being minus, and if we continue the effects. So, this table will give you the positive and the negative effects, that is higher effect, lower effect, and from that you will basically have the combined effect as coming as, if you read the last column of this table, which is D, E, F, A, F, G till the last one, which is A, B, C, D, E, F, G. So, that means you are combining them at different levels. The complete defining relationship for the design is obtained by multiplying the 4 generators, which we have seen, which is ABD, ACE, BCF and ABCG into 2 at a time. So, and then 3 at a time, 4 at a time, and it can go on depending on the number of such combinations which you have. So, the I, which is the so called combined factor, the indicators are, and the combined the mentioning of the factors are, the first one is ABD, ACE, BCF, and it goes on till the last one, which is ABCD, EFG. To find the aliases or the effects of this combined factors, what we do is that we simply multiply the effect by each one in the defining relationship. For example, the aliases of B's would basically be, as we have seen, would be the combination of ABFG, BD, I am reading the last line only, ABFG, BDEF, ABDEG, BCEFG, DFG and ACDEFG. So, based on that you can find out for A, for C, and as you increase K, they would be different combinations. So, if you assume the 3 factor and a higher interactions, then the effects are A would be in the level of A, BD, CE, FG. Similarly, for B it will be B, AD, CF and AG, and combined to the last effect for G it will be G, CD, BE, F, AF, AF. So, I am not going to the details how you do it, but once you make a calculation of the number of factors and how you going to combine them, you will come up with this tables and the combined factors very easily, fractional factorials very easily. So, the saturated model is 2 to the power 7 and suffix 3. So, design which we have already considered. So, it can, and table 18.19, 8.11 which we have already discussed can be used to obtain the 3 design models for studying the fewer of these 7 factors. For example, to generate a design for 6 factors, we may simply drop any one column as given is 8.19. So, let us consider the design with the generator. So, the generators I's are ABD, ACE and BCF. So, again you have the same fundamental principle of layout of the table. The first column is basically the runs, the basic design factors which you have considered is A, B, C. It could be increased or decreased. If you remember, I keep repeating this. And the other combined factors were D, E and F. So, similarly, we have seen that the by finding on the effects, we have found out the, and considering the design of the generators being as ABD, ACE and BCF, you have the combined effect coming as DEF, AF and the last one being, the second last one being BCF and ABC, DEF. So, continuing the discussion, fold over or resolution 3 factors to separate aliased effects and separate them in such a way that we are able to find out the individual as the combined effects also. So, by combining fractional factorial design in which certain signs are switched depending on plus and minus or the effects changing, we can symmetrically isolate effects of the potential interest of the factors and make a judgmental decision about that, such that the accuracy of your combinations of the effects of the factors is maximum. This type of sequential experiment is called the fold over. So, they basically you fold over or take the information set in such a way that you could keep repeating step by step and go forward and combine them. The aliased structure for any fraction with the signs for one or more factors reversed is obtained by making the changes in the signs of the appropriate factors and in the appropriate way, such that the aliased structure of the original fractions can be obtained accordingly, still maintaining the accuracy and the predictive power. So, consider the 2 to the power 7 minus 4 design. Suppose that along the principal factors a second factorial design with the sign reversed is given and then the columns. So, thus this column of D would be in this combinations minus plus plus minus minus plus plus minus minus. So, the different combinations can be done. So, the effects may be estimated for the first factors as shown here. So, these are we can find out for A. So, consider we are mentioning as A transpose, even though that is a symbolic notation. You have A, then you have the effect of BD on the negative side, that means lower, then CE and FG are positive. Similarly, if we go to E prime, again nomenclature way I am saying that the effects of all the first three, which is E, AC and BG are positive and DF is negative. Similarly, you can basically find out the effects of all the so called factors where the change of the signs has been incorporated, considering the fold effect is considered. From the two linear combinations of the effects, so you will basically have, you are now basically trying to take the without the fold and with the fold, but in this case you are going to consider the change in the sign effect. So, it can be done in different ways. If you take two different combinations of the change effects of the signs, it will basically be trying to find out the average value. If you take three such sign effects changes in combinations, it will be 1/3. So, you are putting equal weightages of the signs in order to find out the overall effect of the fold and the fractional factorial design. Now, remember that this probabilities which you are giving half or 1/3 depending on 3 different combinations sign change or 1/4 for 4 different sign changes, we are giving equal probabilities to the sign change. It may not be true in actual practical examples. So, obviously, it will change depending on how the problem and how the overall conceptual framework of the problem formulation has been done. So, in this case, if you consider again the I's, which is basically I's means the overall combined effects of the basic factors and their actual combined effects combined factors which you have. So, sorry for repeating the word. So, you have basically ABC, and then if you remember, you have combined them as AB, AC and BC, then you consider the combined effect of ABC. So, which we mentioned as DEF for the first one, which D was basically for AB, then E was for AC and F was for BC and G was for ABC. So, this the first column gives you the basic factors along with their combined factors. Then from the combination of the this fold effects, you are considering one sign change. So, original plus the one sign change, you found out the average. So, averages values which is given in the second column are for one case is basically for A, it will be A plus CE plus FG. Similarly, for B, it will be B plus CF plus EG. Similarly, if you go to the last one, which is G, it will be G plus BE plus AF. So, these words which I am mentioning are the combined effect of the factors. So, from a combination, if it is a negative sign, so the combination basically gives me. So, the third column BD for A, AD for B, DG for C, until the second last one is for F, which was initially for the positive sign change, was for the fold effects was F plus BC plus AC AG. Now, it is only DE, which is where I am hovering my finger, and the last one for G, which was for the positive fold effects, was I am using the word positive fold effect in order to make you understand. It is not an actual technical word. It was G plus BE plus AF, and for the other combined for the negative fold effects was basically CD. Thus, we have isolated the main factor of D and all of the two factors interactions and made the best possible combinations. In general, if we add to a fractional design of resolution 3 or higher, so it can be 3, 4, 5, 6 whatever, a further fraction with the sign of a single factor is reversed, then the combined design will provide the estimates of the main effect of that factor and its two factor interaction correspondingly. So, consider these combinations which I did mention in the last slide, I will again repeat it. So, for the 3 factor, so 3 means 3 suffix or the 4 or the 5 when you are considering the fractional factors. So, the factors may be 3, 4, 5, 6, but the level of accuracy which you want 3 or 4 or 5 would basically be dictated by the combinations which you are going to take. If it is 3, that means you are going to take the combinations of 2 at a time, 3 at a time. If you are going to consider the 4 so called factors being considered to a 2 level, so you will only consider 2 at a time, 4C2. If you are considering say for example, k number of factors in p such combinations. So, obviously, it would be go as Kc2, Kc3 till Kcp. So, and combinations can be done accordingly depending on the accuracy we want. But for all of these, if you consider the fold effect, obviously this change of signs would increase correspondingly. So, if you want to basically make an accurate calculations, obviously the question would be asked that to how many different such combinations of folds, different combinations of factors, different combinations of combining these factors would be taken into consideration. So, which you have to decide depending on the problem which you are going to solve. So, if I say that and repeat it, and obviously calculations would entail a lot of time. So, whether you want to ask your question whether it really suits your time and effort and energy to do such a detailed calculation and get a result, where the effect may not be that substantial. So, obviously you will lessen the amount of calculation to get the best effect in the least possible time, because that entails energy, time, money, so on and so forth. So let me repeat it. So, in general, if we add a fractional design of resolution 3 or higher, a further fractional with the signs of single factor is reversed, then the combined design will provide estimates of the main effect of that factor and its two factor interactions accordingly. This is sometimes called a single factor fold over model. So, it can be single, double, triple depending on number of such folds you are doing different combinations. Now, suppose we add a resolution 3 fractional second fractions in which the signs of all the factors are reversed. So, this reverse or combination of the factors signs can be done depending on the problem layout. This type of fold over sometimes called a full fold over or a reflection fold, or depending on what combinations of folds you are taking, it breaks the Aliased links between all the main effects and their two factor interactions, such that even if you are trying to do a detailed calculation, what you are actually aiming at is to basically break up these effects and try to find the individual factors or individual combination of factors, such that our accuracy increases in order to predict the overall effect of the fractional factor models. So, let us consider an example. I will read it and then come to the one. So, a human performance analyst is conducting an experiment to study eye focus time and has built an apparatus in which the several factors can be controlled during the test. The factors he initially regards as important are acuity or sharpness of the vision, which we mention as factor A, distance from the target to the eye. So, you are basically checking the power of the eyes and doing all the test, which is distance from the target which you want to the eye want to see, or you want the patient to see, or the experimenter wants the persons on whom they are doing the experiment to see, that is B. What is the target shape depending on how this model is being developed. So, smaller the size, larger the size, obviously you will have an effect on your eye. So, what is the illumination level in lumens, whether the room is bright or dark. Then you take this target size. So, apart from the target shape, which is how it is designed, the size is also important. Then the target density, how consider you are seeing a picture, and if it is very dense color, the number of pixels are very large, obviously it is much better visible. If it is very light, obviously it becomes difficult. So, if you have a screen, computer screen far off, or a TV screen, so the density of pixels or density of number of such dots per square inches per square centimeters would basically entail you in much better visibility of that screen, whatever the pictures, whatever the objects which are there on the screen. And the other factor is basically the subject. So, you have basically A, B, C, D, E, F, G such individual factors. So, two levels of each factors are considered. So, the experimenter suspects that only a few of these 7 factors which he have considered A to G are of major importance for the study, and that higher order interaction between the factors can be neglected. So, say for example, you combine A, B, A, C, or if you combine A, D, E, whatever the combination. So, obviously, you can combine 2 at a time, 3 at a time, 4 at a time, and continue till the highest level. On the basis of this assumption, the analyst decides to run a screening experiment to identify the most important factors, and then to concentrate further and do the analysis in more details. To screen these 7 factors, he or she runs the treatment combinations from 2 to the power 7 minus 4 or the third level design in as given in table 8.19 in random order in order to obtain the focus time on the on a level of milliseconds, and that is given in the table 8 as given here, which is table 8.21. So, what you have is 7 factors and you are considering a level p value of 4 and through the third level of so called accuracy. So, this is designed for the eye focus time experiment, which say for example, the ophthalmologist or the optometrician or the doctor is doing. So, the combinations are given. So, you have basic factor designs. Technically, they were combined as A, B, C. So, the other factors are D, E, F, G, which we consider as the combinations of A, B, which is for D, E is basically A, C, B is B, C, and G is A, B, C. So, if you do the runs which are given in the first column, run 1 to 8, and if you combine them, the combinations are given as, say for example, for the first row you have the runs as the values of A, B, C are minus and the values are given, and then you find out the combinations of D, E, F, G as positive, 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 minus respectively, and the time is given in the last column. That means, you are trying to find out the time of the focuses and all these things in milliseconds. Similarly, for the second run you take a different combinations where effect of A is positive, B, C is negative, and the combinations of D to G can be seen from this table. Similarly, for the third, fourth, fifth till the eighth one, when you are considering all the effects are positive and the time in milliseconds are given in the last column. The 7 main effects of this aliases may estimated from this data. So, they are as mentioned. So, the equations can be found out and we see the effects and the aliases as follows. So, for A, you have the value of 20.6. I am just repeating, those are in the milliseconds, and the effects are for AB, BD, CE and FG. Similarly, for B, the B I am talking about the so called the combined effects. So, it is B, AD, CE and EG. Similarly, for third, fourth, fifth, sixth, seventh, which are the combined effect of C, D, E, F, G respectively, the effects the values are given as minus 0.28, 28.88, minus 0.28, minus 0.63 and minus 2.43, and the values are individually are given. For example, if I want to find out, so what I will do is that I try to find out the effects of for A combined would be for A, BD, CE and FG. So, if you put those values of the milliseconds which you found out, so how many such combinations are there? There are 4. What are those 4? A, BD, CE and FG. Hence, you will basically give a weightages of 1/4. Based on them, when you calculate, you find out the value of 20.6. So, you can do the calculations accordingly. The 3 large effects which are basically the combined effect of A, combined effect of B and combined effect of D are found out. The simplest interpretation of the results of the experiment is that the main effects of A, B, D are all significant and you will consider them accordingly. However, the interpretation is not unique, because one can also logically conclude that different combinations of A, B and A, B interpretation, or perhaps interaction of B, C and D interactions and different combinations can give you the same effect. So, notice that the ABD is in defining the relationship for the 2 factor F 7 minus 4 to the level 3 accuracy can be done accordingly, and we can basically do the calculations and find out the so called models and do it. So, with this we will end the 20th lecture and continue more discussions about the factorial models, the 4 models and so on and so forth in the next remaining 12 lectures. Have a nice day. Thank you very much.